please.
Correct. So I've selected one story for this talk, and I'm not mentioning any other activities. But, hope this fits in well. So to tell this story, I'm going to first start with the introduction to trapped polarity on condensates, and then persistent vorticity and chains and traps, chains and lattices of such condensates. And then after the original part, I'll quickly conclude. So we are studying an optical microcavity in a strong coupling regime that is non-resonantly pumped. That is, electron hole pairs are injected, then they eventually relax and form an incoherent reservoir of excitonic-like particles close to the bottleneck of the exciton polariton dispersion. And then eventually, if the pumping is strong enough, a coherent condensate part is formed close to the ground state, close to the bottom of this dispersion due to stimulated scattering. And we are also considering the highly non-equilibrium case where the thermalization is much slower than the lifetime, the rate of decay of polaritons. So now, if the reservoir is spatially non-uniform, if it, for example, has the shape of a ring, then the condensate actually forms inside this ring by the particles that slide down the potential barrier. And the reservoir provides not only the trapping potential, but also the feed for the condensate. And typically, it actually forms in the excited state, the highest excited confined mode of this potential trap. And naturally, depending on the shape of this trap, you can have formation of a bosonic condensate in higher order modes confined in a trap. And then for a circularly symmetric trap, it is known that the condensate forms in a vortex mode. So these are simulations that show that the phase is rotating around the center. And the simplest model that captures this behavior is based on the extended Gross-Pitaevsky equation, where the decay and incoming particles from the coupled reservoir are included phenomenologically. So then this model can be projected onto two-mode basis, and then it's even simpler than that. So you can describe the dynamics of a condensate in terms of the evolution of a certain pseudovector S, whose length corresponds to the population of the condensate, and direction corresponds to its internal degree of freedom, which is in this case the orbital momentum. And now it is important that, well, this equation has a gain dissipation competition term, let's say, and the rest is just spinor precession in a certain effective magnetic field that is similar to self-induced Larmor precession. Then, depending on the size of this ring-shaped trap, the actual value of the angular momentum can also vary, and it is captured by a simple delta shell non-Hermitian potential model. So the higher the size of the trap, the higher the angular momentum and the vorticity. Right. So for details, I'm actually addressing you to the talk by Alexei Yulian on Friday. Then, in the case of the chain of such trapped condensates, even in the linear regime, there is something interesting. So first, if you place two trapped condensates in the vicinity of each other, it breaks the circular symmetry and hampers the formation of vortices. So naturally, condensates tend to form in dipole states, but even in the linear regime, there is something interesting, and there are different kinds of linear bonding. So it can be either pi or sigma types, which kind of mimics bonding of electrons in molecules. And in the case of lattices, and these are experimental figures, the symmetry is partly restored. And in the case of this triangular lattice of trapped condensate, they also form vortices. And an interesting question that arises is whether or not the direction of vorticity in this lattice is somehow ordered. There are signs that it is. So that is the first question. And the second is whether or not there is something topologically interesting in this lattice. And I'm going to answer both questions, and I'll try to answer both questions in the second part of my talk. So we are starting with basically the same kind of equation, extended Gross-Pitayevsky equation with included quasi-stationary density of the reservoir in the adiabatic approximation. And then for the single trap, the solution is simple. It is described in terms of Bessel functions and Hankel functions in the linear approximation, and projecting the total wave function of the condensate onto the basis of such states, we can construct a discrete tight binding like model for a couple of traps. The Hamiltonian is 4 by 4, and it depends on a couple of coupling parameters, two coupling parameters that are first is spin independent J, and then this figure J is for the spin anisotropic coupling parameter. And then direct calculation of this coupling parameter shows that actually the relative value of imaginary parts of this coupling parameter that are responsible for the choice of the mode, so the dissipative mechanism. So that alternates. You can end up with either ferromagnetic type bonding or anti-ferromagnetic type bonding, depending on the distance between the traps. And so to answer the second question of topology, we analyzed the honeycomb lattice because it's the easiest system in which we could get something topological non-trivial. And so we constructed a Bogolyubov matrix for excitations, for the spectrum of excitations of ferromagnetically coupled condensate state, and by diagonalizing this matrix, obtained the following spectra and the following topological transitions that show that following topological transitions. First, in the strengths of the effective spin orbital coupling, and second, in the value of the effective field that is present in this system, which is basically the density of the condensate, and the emergence of these topological edge states, and the varying number is reflected in the non-zero band-Berry curvature and associated Chern numbers. So just a couple of conclusions. We predict ferromagnetic or anti-ferromagnetic ordering of vortices in a lattice of such polarity vortex condensates, and also predict topological transitions in the absence of any real magnetic field. And as for the outlook, we can also, I'm interested in studying how to control the spontaneously, the otherwise spontaneous topological transitions and also consider the case where the model is not PT symmetric and is fully non-Hermitian. So I'd like to thank my co-authors, Stella Hyson, Helgi Sigurdsson, and Paulos Rigudakis, and also thank Russian Science Foundation for funding, and say that mention that this grant is being transferred to Obrikowski Center for Theoretical Physics. And with this, thank you for your attention.
Thank you very much. Maybe I will start with a short question. So Anton, I didn't fully understood which parameter controls your transition between ferromagnetic and antiferromagnetic coupling.
So it's the distance. It's the distance between the two traps. So here the coupling parameters are plotted against the normalized distance, and it shows that if you compare the two matrix elements J and this figure J, the relative value is alternating depending on the distance. So you can have alternation between the two regions, ferromagnetic and ferromagnetic.
High angular momentum, yes, because the special function oscillates.
Yes, exactly. So actually, this dependence reflects Hankel function.
Okay.
Yeah.
Okay. Other questions, Alexei, please.
So in the antiferromagnetic case, on a triangular lattice, you should have frustration of antiferromagnetism and probably a lot of solutions that would have the same energy, like or close energies. So the generate solution. So how the system knows which two?
Good question. I think that in this case, we would have time. We can potentially have a time-dependent solution. Remember that this is a non-equilibrium system. The stationary state of the condensate is not necessarily the ground state, and it may be the case that it evolves in time. So we may have something like a limit cycle periodic evolution, for example.
Do you see it in your simulations?
Not so far not, but we didn't study the anti-ferromagnetic behavior, and this is an interesting question. Thank you.
But you study hexagonal lattice, not a trigonal one.
Yes, true hexagonal and the ferromagnetic coupling. So the simplest possible case where we expected something topologically non-trivial, and the message is that it is there.
Что играет основательное решение, что играет роль магнитного поля? То есть что является тем вектором, который...
А вот это очень интересно. Значит, мне очень жаль, что мне не удалось это донести, но я, во-первых, могу здесь сослаться на доклад Алексея, потому что он там рассказывает, в том числе про наши вместе с ним работы. Но идея в том, что нужно две вещи. Нужно, значит, диссипация и накачка, и нелинейность. Вот, две эти вещи в итоге дают спонтанное нарушение симметрии, что похоже на фазовый переход второго рода.
То есть вы хотите сказать, что спонтанно нарушается либо так, либо так?
Да.
То есть это не то, что вынужденно.
Он говорит, что как в ванне, куда закрутят.
Типа того.
Понятно,
ну, дипломатично в ванне, я бы сказал, в другом сантехническом изделии. Ну да, закручивается.
Или еще вопросы?
Ну, там, кстати, не совсем спонтанно.
Это тоже правда.
Это вранье, это легенда.
Я проверил.
У неба полушарных исследователей, да, лево, вправо полушарных, вправо.
Ну да, это как в бассейне, когда система неравновесная, есть труба на вход и труба на выход. И там могут формироваться такие вихревые решения.
Okay, so if there are no other questions, let us thank the speaker, and let us thank all those who officially presented for the reports. And now we have last but not least presentation by Vanik Nazarian. We do not need to evaluate him, but he will just provide an account of his research activity.